Today, we are taking a fascinating and really extensive look at an object that was arguably the most guarded secret of World War II. An instrument synonymous with the very promise of surgical strategic warfare, the Norden Bombsight.
Yeah, this is a real deep dive into, myth versus mechanics.
Yeah.
The Norden sits right at that intersection of, well, brilliant mechanical genius, intense propaganda, maybe necessary propaganda, and just sheer messy battlefield chaos.
Right.
We've pulled together sources that really peel back the layers of that wartime legend, showing us that the device was truly revolutionary for its time, yet arguably it never quite lived up to the almost mythical expectations placed upon it.
Especially by the strategic planners, right?
Exactly, by the planners.
That's our mission today, then. We need to contrast those legendary, almost absurd claims, the pickle barrel accuracy, with the complex, often frustrating reality faced by the, tens of thousands of crews who relied on it?
Tens of thousands, yeah. And this story really begins right at the dawn of modern air warfare, when the whole concept of strategic bombing was still pretty theoretical.
So taking us back.
That shift, you could argue, happened pretty decisively in 1921. Before then, battleships ruled the seas. That was the accepted wisdom.
The capital ship.
The capital ship. But then General Billy Mitchell's airmen, they conducted this groundbreaking test bombing the former German battleship Ostfriesland. Now, the key detail here, you have to remember, is the ship was huge and completely motionless, anchored off the coast.
Ideal conditions.
Absolutely ideal. And despite that, it still took 65 bombs, dropped over quite a long period, to finally sink it.
So it took significant effort, a lot of explosives, but I guess the visual, this giant warship going down because of aircraft, this is enough to just shatter the old way of thinking.
It absolutely was. The message was crystal clear. Air power could challenge the primacy of the battleship. This wasn't just about sinking one ship. It fundamentally shifted strategic thinking. Post-World War I, the military planners were desperately looking for ways to avoid a repeat of that horrific static trench warfare.
Understandably.
Yeah, the slaughter that defined that conflict.
And the solution they landed on was moving the battle away from the front lines entirely.
Right. The new doctrine became strategic bombing, taking out the enemy's ability to fight by, theoretically, surgically destroying their industrial heartland.
Things like manufacturing centers, transport hubs, power infrastructure.
Exactly. They were trying to destroy a nation's ability to wage war without these huge, costly land battles. A sort of knockout blow from the air.
But, okay, you can't destroy one specific factory like a ball bearing plant or a single power station with just guesswork bombing, can you?
No, absolutely not. This new doctrine absolutely required genuine, predictable precision. And it had to be achieved from high altitudes and high speeds conditions that were being engineered into the new generation of aircraft, like the B-17 Flying Fortress.
Which were coming online.
Exactly. And the existing technology, those sort of crude WWII sites, they simply couldn't deliver that kind of accuracy. So the need for something like the Norden was born out of this strategic, almost existential demand for precision.
And out of that intense demand came the legend, heavily promoted, you mentioned, by the company itself and the military, probably to boost public morale.
Oh, absolutely. The claim that everyone remembers, the one that really stuck in popular culture, was that a bombardier using a Norden could hit a pickle barrel from 20,000 feet.
The pickle barrel, it's iconic.
It's arguably the greatest piece of wartime marketing ever devised. They even backed it up with this rather brilliant, sort of high-minded Latin motto meant to cement this idea of almost godlike accuracy. Cupa fiat melior mirie per Norden obibut.
Okay, I need the translation for that one. It sounds impressive.
It is. The literal Latin translates roughly to, may a better pickle barrel be made. Through Norden, it shall also be destroyed. Or maybe, when better pickle barrels are built, Norden will hit them too.
Wow.
It wasn't just a boast. It was a statement of, inevitability. A promise that the technology was essentially flawless. It convinced the public, sure, but perhaps more importantly, it convinced military leadership.
Yet, the sources we looked at tell us that the physical reality of that claim is, almost absurd. Even if the device worked perfectly, could a bombardier actually see a pickle barrel from 20,000 feet?
No, not a chance. From that altitude, 4 miles up, the target would be completely obscured by the sight's own crosshairs. The idea that you could visually acquire and lock onto something that small is just It's not physically possible.
Right.
And that exaggeration, that huge gap between the promise and the physics, that really becomes the central tension of the whole Norden story.
Okay, so our central thesis then, supported by the sources, is that the Norden was brilliant for its time, but it really failed to deliver on these, frankly, impossible expectations. Yeah.
And the reasons were a whole mix of issues. Inherent mechanical errors, maybe some specific poor design choices by the inventor himself.
Definitely some of those.
The incredibly complicated physics of a falling bomb, the extreme hazards of combat, poor training maybe, reliability issues. It's a long list.
The confluence of factors, exactly. The legend was, an essential piece of wartime secrecy and morale boosting, but the reality on the ground, or rather in the air, was messy and incredibly complicated. And to understand that complexity, I think we have to start with the man who built it.
Right. Let's transition now to Carl Lucas Norden, the designer and the engineering puzzle he was trying to solve. Norden sounds like quite an unusual character, wasn't he?
Highly unusual, yeah. Born in Java in 1880, he was classically trained as a mechanical engineer at the prestigious Swiss Federal Polytechnic Institute. And here's an interesting historical side note. While he was there, he actually overlapped with another famously disciplined, maybe irascible student, Nikolai Lenin.
No kidding. Lenin and Norden. Yeah, small world, right? Anyway, Norden immigrated to the U.S. in 1904, bringing with him this very particular set of skills and, well, let's just say a challenging personality.
Okay. He started out at Sperry Gyroscope Company, right? Working on ship stabilization systems. That explains his deep knowledge of gyroscopes, I suppose.
It does. That was crucial background. But it seems his difficult temperament quickly led to conflict there.
How so?
Well, the reports say he was notorious for being self-centered, impatient, domineering, extremely abrasive, a complete driven perfectionist. Navy personnel who had to deal with him apparently earned him the nickname Old Man Dynamite.
Old Man Dynamite, okay.
Yeah. He eventually quit Sperry over a bitter salary dispute with Elmer Sperry himself and struck out on his own, forming the Carl L. Norden Company. He was determined, it seems, to build a perfect machine his way.
It sounds like his personality was kind of his genius and his flaw all wrapped up together, so driven by perfection that he refused to use methods he didn't personally approve of.
That's absolutely right. And he had this very peculiar, almost philosophical view of his own role. He insisted he was a designer, not an inventor.
Why the distinction?
He believed, apparently quite sincerely, that only God could truly invent. Humans could only design, using God-given principles. This sort of deep-seated aversion to self-promotion meant that his name didn't even appear on the patent for his most advanced bomb sight, the Mark 15, the M9, the very instrument that made his company famous.
That's strange.
It is. He wanted the machine to stand alone on its merits, reflecting his, high ethical standards, even while his abrasive style alienated pretty much everyone he had to work with professionally.
Given that level of irascibility, Old Man Dynamite, it actually makes sense that the Navy eventually stepped in. They felt they had to impose some structure on his operation.
They did, yeah. The project was just too vital to leave entirely to him and his temperament. The Navy mandated that he bring in a partner.
Okay, who is that?
A man named Ted Barth. Barth had a background in manufacturing, and crucially, he possessed the business savvy and, perhaps more importantly, the diplomatic skills that Norden completely lacked.
Ah, the classic partnership. Norden and Barth. That sounds pivotal. Norden handles the mechanics, the genius, the complexity.
Right. The pure engineering.
And Barth becomes the indispensable promoter, the one maybe responsible for aggressively marketing the bomb site and generating some of those enduring, perhaps misleading legends we talked about, like the Pickle barrel.
It seems likely Barth played a huge role there. He understood that perception was everything, especially during wartime. He bridged that gap between Norden's demanding, uncompromising design process and the political and military world that desperately needed to believe in the device's infallibility.
Okay, so let's talk about the technical puzzle Norden was actually trying to solve. What is the fundamental ballistic problem that any bomb site, any system like this, has to overcome?
Okay, the fundamental problem is timing.
Right.
Specifically, solving for the exact moment, what they call the range angle, when the bomb must be released to hit the target. Think about it. A bomber flying at, say, 25,000 feet, which was a common operational altitude.
Yeah.
The bomb would take roughly 30 seconds to fall to the ground.
Half a minute.
Half a minute. In that time, the aircraft has traveled several miles horizontally. And meanwhile, the wind, the air temperature, the air density, They all affect the bomb's trajectory as it falls.
So you need some kind of pre-programmed ballistic calculator inside the sight to figure out where the bomb will actually land relative to where the plane is right now.
Precisely. And what data does that calculator need? Well, you need 5 major inputs. Some are constants, some are dynamic.
Okay, what are they?
Constants include the bomb's specific aerodynamic characteristics. These dictate the trail, basically, the amount of horizontal distance the bomb loses due to air resistance as it falls. Then the dynamic inputs. You need the plane's precise altitude, its precise ground speed vector that's speed and direction over the ground.
Which isn't the same as airspeed.
Not at all, because of wind. You also need humidity, and you need to factor in crosswinds, which cause drift.
And that's just the predictable stuff. Then you have the completely unpredictable factors.
Exactly.
Right?
And those are what make the problem nearly impossible for a purely analog mechanical device. You've got things like local variations in gravity, which can actually affect fall time slightly. You've got severe air turbulence buffeting the plane. The fact that the plane is never perfectly, absolutely level.
Evasive maneuvers if they're under attack.
Evasive maneuvers, which throws everything off. And of course, if the target itself is moving, like a ship, all of this data, ideally, needs to be calculated accurately in real time, and the bomb has to be released within a fraction of a second of that optimal moment.
Okay, so how did the early, really crude solutions handle this before Norden came along?
Those were the World War I era timing-type sights. They were often very simple mechanical affairs, sometimes literally just calibrated sticks with crosshairs, maybe a spirit level.
Pretty basic.
Very basic. The bombardier would manually time the plane's speed over the ground using a stopwatch and looking at reference points on the ground below. He'd then input the altitude and some basic ballistic data into his sight, maybe adjust some dials, and then simply wait for the target to line up in his sight at the calculated release point. Then click.
I can imagine that was highly inaccurate.
Terribly so. And one major drawback was, to minimize the effect of drift from crosswinds, the pilot was often forced to fly directly into the wind, correcting constantly to stay on course.
Which means a long, straight, predictable bombing run.
Exactly, exposing the bomber to ground fire for extended periods. Plus, any pitch or roll of the aircraft, or even a slight error in the bombardier's timing with his stopwatch, resulted in enormous errors on the ground, potentially miles away from the target. The Norden aimed to eliminate, or at least drastically reduce, all these variables.
Okay, here's where Norden's genius, the synchronous type sight, comes in. What was the core, the revolutionary technological leap he made?
The key was synchronization. The device itself had to automatically move its line of sight at the exact same speed and angle that the aircraft was moving relative to the ground beneath it.
Okay, how did he achieve that?
Norden achieved this by integrating the sight head, the telescope part, with a mechanism below it that housed a variable speed motor and a rotating mirror or prism in the optical path.
So the motor rotating the mirror in the telescope's light path, how did that help?
Okay, so when the bombardier looked through the scope, he would manually adjust the speed of that motor using 2 control knobs, one for forward-aft speed, one for left-right drift. He adjusted them until the target and the ground directly beneath it appeared absolutely stationary in the crosshairs.
Ah, so by canceling out the apparent motion of the ground.
Exactly. By doing that, the bombardier was, in essence, feeding the bomb sight the plane's precise ground speed vector and drift angle in real time. The sight was measuring it directly.
It effectively turns the sight itself into a kind of ground speed analog computer.
Precisely. That's a great way to put it. Once the target was locked and appearing stationary, the bombardier could maintain that perfect trajectory for a much shorter bombing run. Often less than a minute was needed for stabilization and calculation. The system could then take that measured ground speed, factor in the altitude and bomb trail data that was preset, calculate the cumulative effects, and then automatically initiate the bomb release when the target reached the predetermined range angle.
Conceptually revolutionary.
Absolutely. But applying that synchronization principle demanded engineering capabilities that were really stretched to the breaking point for the time. Mechanical complexity on a whole new level.
Which takes us right into the consequences of Norden's brilliance meeting his personal engineering biases. Let's talk about the machine itself and why its precision was apparently so fragile. We're moving into section 2, the device, its flaws, and operational nightmares.
Right. The Norden sight, officially the Mark 15 for the Navy, M9 for the Army Air Forces, was an absolute marvel of mechanical complexity, no doubt about it. But it was also incredibly unwieldy.
How big was it?
It weighed over 40 pounds, maybe closer to 50 with all its bits. And it was actually a two-piece integrated instrument. You couldn't really separate them functionally.
Okay, tell us about those two pieces.
Right, so you have the sight head itself, the top part, sometimes called the jug by the crews. This contained the sighting telescope, the crucial vertical gyroscope for stabilization against pitch and roll, and all the manual control knobs the bombardier used.
Okay, the jug.
This sat perched, somewhat precariously, atop the stabilizer unit nicknamed the cork, or sometimes the football. This lower section housed a really complicated autopilot mechanism linked to the aircraft's controls. When the bombardier engaged the Norden for the final run, it actually steered the B-17 itself, keeping it straight and level.
Wow, so the bombsight flew the plane.
For that critical final minute or so, yes.
No wonder the airmen had nicknames like the Golden Goose. It was precious, complex, awkward.
Definitely awkward and precious. Inside this mechanical masterpiece, it was almost Baroque in its complexity. We're talking over 2,000 individual components.
2,000 parts.
Yeah, a whole network of intricate cams, potentiometers, specialized gyroscopes running at high speed, finely tuned gears, mechanical linkages, and crucially, 61 highly specialized miniature ball bearings.
61 ball bearings. That sounds like a weak point.
It was a major one, as we'll see. And that automatic release function we mentioned, it was absolutely mandatory because, as we noted earlier, the margins for error were just so incredibly thin.
Yeah.
At a typical bombing speed of, say, 200 mil/h, that level of accuracy required meant that a mere half-second error in timing the release translated to missing the aiming point by 150 feet on the ground.
Just half a second.
Half a second. Human reflexes just weren't reliable enough.
Okay, so this incredible required precision meant that Norden's personal biases, his design choices, became massive operational impediments. You mentioned earlier his aversion to alternating current, AC.
Yes, that was probably his single biggest technical flaw looking back. Norden, really clinging to his older mechanical sensibilities from his ship gyro days, absolutely insisted on using direct current DC motors throughout the device. This was despite superior, more reliable AC motor alternatives being available at the time.
And the problem with DC motors is...
the carbon brushes they use to conduct electricity to the rotor.
Right. And those carbon brushes wear down, they generate dust.
Exactly. Fine carbon dust was constantly being shed by these motors and spreading throughout the delicate mechanism. It contaminated the intricate gears, the linkages, and most critically, those 61 specialized low-friction ball bearings. These bearings were engineered to the tightest possible tolerances. We're talking fractions of a micron. The introduction of fine abrasive carbon dust guaranteed increased friction, binding, and error. It demanded constant, incredibly precise cleaning and maintenance.
Which was practically impossible to achieve consistently in a muddy airfield workshop in England or North Africa.
Absolutely impossible under combat conditions. So, in a way, he built this perfect machine that was almost designed to self-destruct, or at least degrade rapidly, through its own operational necessity.
That's a harsh assessment, but it sounds accurate. What about his second bias, his distrust of electronics?
That was equally damaging, really. He strongly preferred intricate mechanical solutions, complex systems of levers, cams, gears, and mechanical linkages over the faster, simpler, and far more reliable electronic circuits that were actually available, even then. He had essentially designed the world's most complex, most sophisticated mechanical analog calculator right when the age of vacuum tubes and early digital electronics was beginning to dawn.
So his pursuit of purely mechanical perfection, driven by his personal preferences, resulted in a device that was needlessly complicated, inherently prone to error, and incredibly difficult to mass-produce consistently or repair effectively in the field.
Absolutely. The need for those incredibly close tolerances, especially in the gears and bearings, exceeded the capabilities of many mass production facilities brought online during the war. This led to significant quality control problems. And when things broke, which they frequently did, parts often weren't interchangeable between sites. It created logistical nightmares for the ground crews trying to keep these things operational.
Okay, now let's put that incredibly complex, temperamental machine in the hands of the person who had to use it under fire. Brigadier General Eugene Eubank apparently called the bombardier the most important of our fighting men.
And arguably he was, for the strategic bombing mission at least. The bombardier's role was unbelievably challenging. As we said, they were often isolated way out front in the exposed plexiglass nose of the aircraft, the greenhouse, which unfortunately led to it being one of the most dangerous positions with one of the highest injury rates in the entire crew.
And the mental and physical demands of just setting up and operating the Norden site while under extreme duress.
Immense, just immense.
How rigorous was the training for them, and how did that training accuracy compare to what they actually achieved in combat?
The training was pretty intensive, lasting up to 18 weeks. To attain the coveted title of Distinguished Bombardier, which meant you were top of your class during these controlled peacetime practice runs.
Yeah.
You know, flying straight and level, no flak, no fighters.
Ideal conditions again.
Right. The airmen had to achieve an average circular air of just 172 feet. That was the benchmark of excellence coming out of training.
Okay, 172 feet. That sounds pretty good on paper. But if the strategic goal was truly precision bombing, hitting specific factory buildings, maybe rail yards, individual structures, was 172 feet actually accurate enough?
Well, that's the critical question. And the answer is probably not, or at least not reliably. While 172 feet sounds impressively accurate, it was often still too great an error to reliably disable a small, hardened target, like a specific machine shop or a power generator building. And crucially, our sources consistently show that performance in real combat was inevitably much, much worse than those 172-foot training metrics.
So this was maybe the first big hint that the whole pickle barrel myth was placing an impossible burden on these airmen.
I think so. It set an expectation that reality just couldn't match.
Okay, so let's imagine this scene. The bombardier is hunkered down in that freezing cold nose. The aircraft is vibrating like crazy, engines roaring, maybe flak is starting to burst around them. And they have to start the dozens of setup steps for the Norden. What was the critical first step?
The absolute critical first step before anything else was leveling the gyroscopes inside the stabilizer unit, the cork. He had to do this using two problematic bubble sights, basically sophisticated spirit levels mounted at right angles to each other.
Okay, like a carpenter's level, but more sensitive. Why were they problematic?
The difficulty was twofold. First, the bubbles themselves were highly affected by the wildly varying ambient temperature in that unheated, unpressurized nose compartment. The cold could change the bubble's size and how sluggishly it behaved. Second, just imagine trying to precisely read a minute bubble, get it perfectly centered, while the whole plane is vibrating violently and maybe even maneuvering slightly. It was nearly impossible to guarantee the gyros were perfectly vertical.
And if the gyros weren't perfectly vertical from the start?
The entire calculation downstream was immediately flawed. Garbage in, garbage out.
Right. So after somehow leveling the gyros, they then had to input all the ballistic parameters using external tables and maybe some mechanical calculators.
Exactly. They'd use slide rule-like handheld computers like the E6B flight computer and pre-calculated bombing tables to determine the key variables for that specific mission and bomb type. Then they'd manually preset those values on the dials on the sight head. The time of fall, which is mainly related to altitude, the trail, based on the bomb's specific aerodynamic drag, and the drift, based on observed or predicted crosswinds. He also manually preset the crucial dropping angle based on these calculations.
Okay, setup done. Then comes the final incredibly intense minute or so of the actual bombing run.
Yeah, this is where the tension peaked. The bombardier had to take control of the aircraft, engage the Norden's autopilot, which runner steers the entire B-17, and then make dozens of incredibly fine-tuning adjustments. He's constantly looking through the telescope using those two main control knobs, trying to synchronize the speed of the sight head's internal motor with the actual ground speed he's observing.
So he's trying to cancel out the forward-aft motion and the sideways drift simultaneously, keeping those crosshairs absolutely dead centered on the aiming point.
Precisely. He's effectively steering the plane by tiny adjustments on the bomb sight control knobs, while simultaneously refining the internal calculations, all while under extreme physical and mental stress. Noise, vibration, cold, fear.
And the site itself is doing the final calculation.
Yes. That entire complex array of gyros, cams, motors, and gears is working towards one singular goal, slowly, precisely advancing a single indicator needle until it matches the predetermined dropping angle that the bombardier set earlier based on his calculations. When those 2 points match the calculated angle and the current sight angle, boom, the bomb sight automatically triggers the electrical circuit to release the ordnance.
So the human element wasn't timing the drop, but getting the synchronization perfect and the initial setup right.
Exactly. Synchronization and setup. That's where the human skill and potential error lay.
The operational problems just in the air sound horrific, even before you factor in enemy action.
They were brutal. We mentioned the cold already. Temperatures in those unheated, unpressurized B-17s at 25,000 or 30,000 feet could easily reach -40 degrees Fahrenheit, sometimes even colder.
-40.
-40. This caused the specialized lubrication oils used in the Norden's intricate mechanisms to congeal, to get thick and gummy. That slowed the delicate gears, caused mechanical lag, introduced errors. The optics, the lenses in the telescope would frequently fog up or frost over.
So what did they do?
The Army Air Forces actually had to develop and issue custom-fitted electrically heated blankets specifically for the bomb sites. They treated them almost like precious cargo that needed to be kept warm, just to ensure they didn't literally seize up mid-flight.
Wrapping the bomb site in an electric blanket. Incredible.
Incredible, but necessary.
And the human factor remained a major source of potential error, didn't it? Even for the smallest involuntary movement by the bombardier.
Absolutely. Think about it. The entire system relied on the bombardier maintaining an absolutely consistent viewing position relative to the eyepiece for the duration of that final run. One source we looked at mentions that if the bombardier involuntarily rose just slightly from his seat, maybe startled by the noise, or a burst of nearby flak jarring the plane, that minor shift in his eye position could subtly change the optical path through the sight.
And that could throw off the calculation.
By hundreds of feet on the ground, potentially. The system was just too sensitive, too analog, too reliant on perfect human interface for the violent, chaotic environment of aerial combat.
That truly emphasizes the point you made earlier. It was like an analog computer designed for laboratory conditions, being asked to perform in, well, hell.
Pretty much sums it up. Designed for a digital world's precision, but built with analog parts and battlefield conditions.
Okay, let's transition now into the non-technical issues, which seem just as critical. We're moving into Section 3, focusing on how politics, propaganda, and this intense security paranoia created just as many obstacles, perhaps, as the engineering itself.
Right, and the first major non-technical obstacle was the, frankly, paralyzing effect of inter-service rivalry. You had the Navy's Bureau of Ordnance Board, they called it, which maintained this rigid bureaucratic monopoly over all bomb site procurement for the U.S. military.
All bomb sites, even for the Army.
Yes. This meant the Army Air Forces, the AAF, who clearly have the greater operational need for strategic bombing in Europe and the Pacific, were forced to purchase their Norden sites exclusively through the Navy.
That sounds incredibly inefficient and just ripe for conflict.
It was apparently a bureaucratic nightmare. Board controlled the allocation schedules, and sources suggest they often prioritized Navy needs first, even when the Navy's operational requirement for high-altitude precision bombing was minimal compared to the AAF's massive B-17 and B-24 fleets heading to Europe.
So bitter disputes over who got the limited number of sites being produced.
Intense, bitter disputes. And the irony is, the Navy apparently rigidly ordered Norden sites for all their standard bombers based on some formula, even when the site was utterly unsuitable for the aircraft's mission. Like putting Nordens on carrier-based dive bombers.
Which couldn't use it properly.
No. Dive bombers couldn't possibly fly the long, straight, level, and consistent path required for the Norden to synchronize and calculate accurately. It was pure bureaucracy dictating equipment procurement, regardless of actual mission suitability. Bureaucratic inertia at its finest, or worst.
Now, I recall the critique we looked at mentioned the Sperry competition. Elmer Sperry's old company, Sperry Gyroscope, they tried to break this Navy monopoly with their own competing bomb sight system, the S-1.
They did. The Sperry S-1 was a serious contender. In fact, it was apparently favored by many within the Army Air Forces because it was, in some key engineering aspects, arguably an improvement over the Norden. It reportedly had a better, more robust stabilization system, used different motor technology, which avoided some of Norden's more rigid design biases like the DC current issue. The AAF actively encouraged its development, seeing it as a way to potentially gain procurement independence from the Navy's board.
So why didn't the S-1 win out then? It sounds like it might have been better.
Several factors conspired against Sperry, unfortunately. They suffered the tragic loss of some key engineering personnel in unrelated accidents at a critical time. Furthermore, there was Sperry's extensive pre-war sales history of similar gyro technology to both Japan and Germany. While there was no evidence of any impropriety related to the S-1, it created a lingering, perhaps unfair air of distrust in some quarters during wartime.
But the deciding factor was?
Logistics, mostly. Wartime production realities simply couldn't handle the massive supply chain burden. The training, the spare parts, the maintenance procedures for supporting two completely different, extremely complex, high-precision bomb sight systems simultaneously across the globe.
So standardization won out, over potential competition, even if the competitor might have had some superior features.
Precisely. In 1943, Washington mandated standardization solely on the Norden design. They shut down the Sperry S-1 production line less than a year after it had really started ramping up.
Yeah.
That moment effectively solidified the Norden's mythical status as the only solution, the chosen one.
And Sperry's reaction?
To this day, apparently Sperry as a company is notoriously silent about their S-1 bombsight involvement. Sources say they simply refer to it in corporate histories as having made other instruments for aircraft during the war, a forgotten competitor.
Fascinating. Now let's talk about the intense security that was wrapped around this device, this myth. You said its existence and supposed accuracy were publicly promoted for propaganda, but the actual mechanics were treated like, what, nuclear codes?
The security was definitely theater, in large part, but it was theater with very real consequences for the people involved. It was classified top secret. The handling procedures were almost paranoid.
Like what?
The site had to be kept covered by that electrically heated blanket, remember. Not just for warmth, but for security. Unless it was actively being used on a mission. It was transported by armed guards to and from the aircraft for every single flight, and stored in secure, locked, often temperature-controlled vaults between missions.
And the most famous part of the security theater, of course, was the bombardier's oath.
Ah yes, the notorious pledge. Every bombardier was formally sworn under threat of court-martial or even execution to protect the Norden site at all costs, and crucially, to destroy it completely if capture seemed imminent.
How were they supposed to destroy it?
They carried specific instructions and sometimes tools detailing destruction methods, putting bullet through the main mechanism using a special thermite-like incendiary device, or if time was really short, physically tearing it out of its mount and tossing it overboard before bailing out. The military was desperately afraid of the enemy capturing one intact and reverse engineering the technology.
But all that incredible security, the oaths, the guards, the vaults, it was breached anyway, wasn't it, by an insider?
It was. A massive counterintelligence failure, really. A German-born draftsman named Hermann Lang, who was working inside the Norden Company's own drafting office, managed to steal the precise plans and detailed specifications for the Norden site.
He just walked out with them.
Essentially, yeah. He was part of a major Nazi espionage ring operating in the U.S. before the war. He sold the blueprints to the Abwehr, German military intelligence, for a reported $1,500. He was eventually caught by the FBI in 1941 as part of the Duquesne spy ring crackdown, convicted of espionage, and eventually deported after the war.
That must have been deeply embarrassing for the U.S. government, and particularly for Carl Norden himself, who is apparently known for his personal distrust of Germans, even while employing many skilled German descent craftsmen in his factory.
Hugely embarrassing. But here's the core irony, according to the sources we reviewed. The stolen plans didn't actually seem to change the course of the war much, if at all.
Really? Why not?
Well, the Germans already had their own sophisticated synchronous bombsight, the Lotfernrohr, often called the Lotfezen. It was also complex, had elaborate optics, and worked on similar principles. While German engineers certainly examined the stolen Norden plans with interest, they ultimately never adopted the Norden design or incorporated its specific features into their own sights.
Why wouldn't they, if it was supposedly so superior?
Because the prevailing German air doctrine, especially early in the war, heavily favored dive bombing and medium-altitude bombing for rapid tactical ground support, think Stukas. They didn't embrace high-level, straight-and-level precision strategic bombing to the same extent as the Allies, especially the USAAF. The stolen technology, brilliant as it might have been, simply didn't fit their primary tactical needs or their aircraft designs. So the entire espionage effort, while successful in acquiring the plans, ended up being functionally moot in terms of providing a decisive military advantage to Germany.
What an incredible twist. All that secrecy, and the enemy couldn't really use it anyway. Okay, let's move to the ultimate reality check. Combat performance. We heard the early demonstrations under ideal conditions were excellent. What was it, 10 out of 12 bombs hitting a simulated battleship target in 1939?
Yeah, demonstrations like that fueled the legend. But that's the sort of tragic story of the Norden, isn't it? The difference between a carefully controlled demonstration with hand-picked crews and ideal weather and the brutal reality of wartime operations over heavily defended Europe. It was catastrophic for accuracy.
So the statistics from actual combat missions are pretty sobering, especially when you compare them back to that pickle barrel myth.
Truly sobering is the right word. Give us the hard numbers. What did the 8th Air Force studies actually find in Europe?
Okay, operational research studies conducted during the war revealed that despite the Norden's sophistication and the intensive training, as few as 5%, just 5% of 8th Air Force bombs actually fell within 1,000 feet of their intended aiming point.
5% within 1,000 feet. That's
Yeah.
not precision.
Not even close. And to make matters worse, the average circular error, which is the average distance between where the bombs actually impacted and the aiming point for typical 500-pound bombs dropped in the European theater, was a staggering 1,673 feet.
1,600 feet. That's over a quarter of a mile on average.
Yes. We're talking about targets routinely being missed by significant portions of a mile, sometimes, according to reports, even by miles, especially if cloud cover or heavy flak disrupted the run. Wow. So that level of inaccuracy meant that the entire original strategic objective of surgical pinpoint bombing, taking out one specific building, was basically failing in practice.
It really was. Strategic planners, fueled by the Norden myth, maybe wanted to hit targets the size of, say, a tennis court, like specific machine shops inside a factory complex, or individual railroad bridges or submarine pens. But when your average error is over 1,600 feet, you quickly realize that true precision bombing just wasn't happening consistently with these unguided munitions, no matter how good the bomb sight was theoretically.
So how did they still manage to eventually cripple the enemy's war machine, which they undoubtedly did? Did they just give up on precision?
They had to pivot tactically.
Yeah.
They largely shifted from attempting true precision bombing to area saturation bombing. They essentially accepted that they probably couldn't reliably hit one specific building, so instead they sent massive formations, often hundreds of bombers, to just carpet bomb an entire district or a whole industrial area, hoping that the collective distribution pattern of thousands of bombs would eventually neutralize the target through sheer volume and statistical probability.
It became a bludgeon instead of a scalpel.
Exactly. A necessary, brutal adaptation to the limits of the technology.
But we do have to acknowledge the incredible difficulty of the task itself, right? Landing even 5% of your bombs within a specific, relatively small area while being shot at miles above the Earth in freezing temperatures. That's still a remarkable feat in its own way, even if it failed to meet that impossible pickle barrel standard.
Absolutely. And one source makes that very fair point. Managing to land, say, an average of 32% of unguided bombs within a larger radius, maybe 1,000 to 1,600 feet, using this incredibly complex, purely mechanical analog computer while operating in extreme cold and under intense enemy fire. That is still a testament to the skill and courage of the airmen and maybe to the device's potential under slightly better circumstances. It highlights the difference between outright technological failure and simply failing to meet unreasonably high expectations set by propaganda.
And they also developed tactical workarounds, didn't they? Training techniques that often superseded trying to use the bomb sight for pure precision on its own.
They did. Recognizing the inherent inaccuracy in the cumulative aero pattern of a large bombing formation, many experienced lead bombardiers were actually trained to intentionally aim slightly short of the designated target point.
Aim short. Why?
Because they knew the bombs released by the following aircraft in the formation would tend to fall slightly later and maybe drift a bit further. So by aiming the lead bomb short, the resulting spread, the bomb carpet, would hopefully walk across the actual aiming point, maximizing the chances of hitting something vital within the target area, even though the primary lead bombardier technically missed his specific mark, according to the crosshairs. It was a pragmatic adjustment.
Clever. And the military also tried to improve the Norden itself, right? By adding various accessories or attachments to overcome some of its inherent limitations.
Yeah, they didn't just accept the flaws, they tried to engineer around them. They developed several specialized attachments to increase its versatility for different missions. There was the low-altitude attachment, the ULDE, mainly for Navy torpedo bombing runs. There was a glide bombing attachment, the GBA, and they also introduced the intervalometer, which became crucial for the area bombing tactic.
Okay, what specifically did the intervalometer do? How did that help with area bombing?
The intervalometer was essentially an adjustable timer connected to the bomb release mechanism. It allowed the bombardier to choose to drop individual bombs from the bomb bay, not all at once in a single salvo, but at precise, preset time intervals, say, half a second apart or 1 second apart.
So instead of one big cluster of bombs hitting roughly the same spot.
You could spread the ordnance out deliberately over a linear distance along the aircraft's flight path. This ensured better area coverage, which was absolutely essential for the effectiveness of saturation bombing tactics. You could create that long carpet of explosions.
Makes sense. And what about dealing with the miserable European weather? Thick clouds must have been a constant enemy for visual bombing.
Oh, a huge enemy. That's where the radar aiming attachments came in. These were perhaps the most critical enhancements, not necessarily for accuracy, but for crew survival and mission completion rates. Systems like the H-2X radar allowed bombing runs to be conducted entirely through thick overcast conditions, which were endemic, just constant in the European theater, especially in winter.
So they could bomb blind, essentially. Did it improve accuracy?
Well, bomb blind is right, but improve accuracy? Not really. The early airborne radar systems were quite imprecise themselves, providing a fuzzy, often ambiguous picture of the ground. So the actual bombing error rate using radar aiming often didn't improve dramatically compared to visual bombing under duress, if anything. Radar bombing was generally less accurate.
But the crews must have appreciated it anyway.
Immensely. Because the ability to fly and bomb through solid clouds meant they didn't have to abort missions nearly as often due to weather, and more importantly, it offered significant protection from visually aimed flak and enemy fighters. It greatly increased the bombers' chances of surviving the mission, even if the bombs weren't hitting the pickle barrel. Survival often trumped pure accuracy.
A crucial development for the air war. Okay, we're moving now into our final section, Section 4, the ultimate test and the lasting legacy of the Norden Bombsight. And the device was present, wasn't it, during arguably the most destructive moments in human history?
It certainly was. The final and perhaps most dramatic operational test of the Norden was over Japan, aiming the first atomic weapons. Major Thomas Farraby, the bombardier aboard the Enola Gay, used a standard Norden sight, serial number V4120, to aim the little boy atomic bomb over Hiroshima on August 6, 1945, dropping from an altitude of 31,000 feet.
And what was Farraby's measured error on that drop, given this significance?
According to the post-mission analysis, Farraby was approximately 800 feet off his intended aiming point, which was the distinctive T-shaped Iowa Bridge in the city center.
800 feet off. Still quite a miss by pickle barrel standards.
Absolutely. And 3 days later, Captain Kermit Behan, bombing from the boxcar, dropped the second bomb, Fat Man, over Nagasaki. He actually missed the intended primary target, the Mitsubishi Steel and Arms Works, by about 1,500 feet, largely due to cloud cover obscuring the aiming point until the last moments.
1,500 feet. So even on these incredibly high-stakes missions, the Norden still exhibited significant error. But in the context of atomic warfare, that inaccuracy suddenly became, well, functionally irrelevant.
Completely irrelevant, yes. The immense destructive power and the massive blast radius of those early atomic weapons rendered the difference between an 800-foot miss or even a 1,500-foot miss and a perfect direct hit almost negligible in terms of the overall devastation cost. The bomb sight's inherent inaccuracy no longer mattered significantly. The sheer, overwhelming destructive force of the ordnance itself guaranteed mission success regardless of pinpoint precision. It was the moment the Norden was effectively made obsolete by the very weapon it was aiming.
A powerful turning point. So the bomb sight's primary operational life was winding down after WWII, but the sheer scale of the investment the U.S. made in it was just staggering, wasn't it?
Absolutely staggering. The U.S. government purchased over 50,000 Norden bomb sights in total throughout its production run. While the typical unit cost was often cited as around $7,500 in wartime dollars, which was a huge amount then.
Equivalent to a car, maybe more.
Oh, much more. But the total program cost, when you factor in R&D, production facilities, training, maintenance, spare parts, everything, it easily exceeded $1 billion in contemporary dollars.
Wow.
A monumental investment in a technology that had arguably already reached its fundamental ballistic limits.
Yet, despite the advent of the jet age and guided missiles starting to appear, the Norden actually stayed in service for quite a few more decades, didn't it?
Yes, remarkably so. Its service life extended well past WWII and even the Korean War. The last known combat use of a Norden bombsight was reportedly as late as 1967 during the Vietnam War.
1967, what was it used for then?
It was apparently repurposed in certain specialized aircraft, likely older propeller-driven types, to drop acoustic sensors along the Ho Chi Minh Trail as part of Operation Eagle White, a rather quiet, almost mundane end for the once legendary golden goose of strategic bombing.
From atomic bombs to dropping sensors. And there is one final delicious historical irony in the Norden Company's post-war legacy, isn't there? Something connecting back to the very targets Norden's bomb sights were supposed to be destroying in Germany.
Oh, it's a profound and almost perfectly poetic irony. Remember we mentioned Norden needed those 61 high-precision miniature ball bearings for each sight. They were incredibly scarce and hard to manufacture to the required tolerance. So Carl Norden and his partner Ted Barth had established a crucial internal manufacturing facility, which they named the Barden Company, combining their names, Barth and Norden, specifically to produce these critical bearings in-house.
Okay.
Well, today, the Barden Company, that direct offshoot of the Norden enterprise, is actually a part of the massive German Avball Bearing Group. And where's FAG headquartered? In Schweinfurt, Germany.
Schweinfurt, the city famous for its ball bearing factories.
The very same city that Norden's bomb sites repeatedly attacked throughout the war, suffering devastating raids precisely because it was the main hub for German ball bearing production. The Achilles heel the Allies were desperately trying to break. The company born from the Norden site is now owned by Germans. In the city the site tried hardest to destroy, you couldn't make it up.
Wow, that's incredible. So the ultimate realization from this whole saga wasn't just about the Norden's specific analog flaws, was it? It's more about the inherent problems facing any unguided munition dropped from high altitude.
That really is the lasting lesson of the Norden story, I think. It underscores that even if you had a device of absolute mechanical perfection, unguided gravity bombs will always suffer from the fundamentally unknowable, unpredictable variables. Tiny variations in bomb aerodynamics from one bomb to the next, unpredictable wind gusts, shifts in humidity and air density across the thousands of feet of fall. The complex physics of the trajectory ultimately defeated the analog computer, not the other way around.
And we see this principle still playing out even in modern conflicts when conventional, unguided munitions are used, right?
Absolutely. Look at the statistics from the 1991 Gulf War, for instance.
Mm-hmm.
Coalition forces dropped about 17,000 advanced precision-guided munitions, laser-guided, GPS-guided bombs with true pinpoint accuracy. Amazing results.
Right.
But they also dropped around 210,000 conventional unguided dumb bombs, mostly from higher altitudes. Guess what the average circular error was on those 210,000 unguided bombs?
Let me guess. Still pretty bad.
They missed their targets by an average of more than 300 feet, which, yes, is better than the 1,600 feet of WWII thanks to better aircraft stability and computers, but it's still only marginally better in the grand scheme of things. Still nowhere near pinpoint accuracy. The basic physics problem persists for unguided weapons.
So the final verdict on the Norden, then, is that it was a truly remarkable technological marvel for its era, the absolute pinnacle of complex mechanical analog computing applied to ballistics. But it fundamentally failed to meet the impossibly high standard of consistent pinpoint accuracy that the strategic planners, maybe fueled by propaganda, demanded of it.
Exactly. True pinpoint accuracy wasn't just a matter of building better gears or cleaner bearings or even better gyros. It really required the advent of guided munitions, smart bombs, which could actively correct their trajectory during the fall, removing those unknowable atmospheric variables from the equation entirely. The Norden was, in many ways, a victim of its own hype, its designers' peculiar biases, and ultimately the hard limits of physics for unguided objects.
This has been a really necessary deep dive, I think, pulling back that heavy curtain on the pickle barrel myth and revealing the incredibly complex mix of mechanical genius, operational chaos, political maneuvering, and human struggle that underpinned the Norden's actual use throughout its long career.
Yet what really stands out to me is how the story of the Norden forces us to confront the fact that technological genius alone is often insufficient, especially when deployed in the harsh realities of war. It was a harsh, incredibly expensive lesson in the physical limitations of what can realistically be accomplished with unguided technology, regardless of how complex and how brilliantly conceived the machinery itself might be.
What a fantastic piece of engineering history, military strategy, and, well, human drama. But that leads us perfectly to our final provocative thought for you, the listener, to maybe mull over after this. We know the Norden was technologically limited by physics and its specific engineering capacity. You know, Carl Norden's DC bias, those unstable bubble sites, the extreme cold congealing the oil in the B-17s, we get that. But given the intense pressure of combat, the security paranoia, and the bureaucratic chaos surrounding it, which of the non-technical factors we discussed do you think ultimately limited the Norden's operational effectiveness the most? Was it the intense secrecy and the security theater that maybe hampered practical use and maintenance? Was it the rigid political bureaucracy and that Navy monopoly over allocation that starved the AAF? Or was it perhaps the domineering, abrasive personality of the designer himself whose biases led to inherent flaws? Secrecy, bureaucracy, or personality, which non-technical factor hurt the Norden most in the field?
Ooh, that's an excellent question to ponder. The human factors often weigh just as heavily, if not more so, than the purely technical ones in these big systems. Which one was the biggest drag? Hard to say definitively.
Something for you to think about. We'll see you next time on The Deep Dive.